Next talk, we stay with the precision measurements, will be given by Dave Weiss, who actually turns out to be the very first graduate student of Steve at Stanford University. And looking forward to your talk, Dave.
Thank you, Joachim. It's a pleasure to be here at this joyous event. I'm going to talk about Steve Chu's physics in general, maybe a little bit of my own work at the end of the talk, and mostly from the perspective of a student, from the time that he first came to Stanford, which was in '87, until when I graduated, which was actually January '93. So I was his first student. For some of you, you're thinking, like, well, wasn't Mark his first student? Mark joined 2 weeks after I did. So I think it's clear that I am the first student, although he did graduate slightly before me as well. Okay, anyway. So, and from the perspective of a student, I'm going to give a list of 4 things which Steve taught me, sometimes explicitly and sometimes just by sort of watching the way he does physics. First thing is that you should use the model of a ball and stick wherever possible. You know, if you have a system which is complicated, maybe it's quantum mechanical, in which case sometimes balls and sticks are hard to apply. But to the extent that you can get a pretty simple physical kind of model, it's useful. So this would be a typical American ball and stick game. There's the stick, there's the ball right there. And I showed this picture. This was the Vector Heads, which was, I think, the last softball team that Steve was on, which was my first year as a graduate student. He was on the softball team. I don't remember what he batted. I think it was near 500. I think he really went out on a high note for softball. So, you know, this ball and stick model, this way to look at physics, which can sometimes, if you take modern physics, can seem a little bit abstract. He has a way or an approach which makes it much more concrete in this instance. So the first work that I knew that Steve had done was a paper that I read when I was a first year on this three-dimensional laser cooling. It's a paper where the heading has been shown a couple of times today. And so this laser cooling in 3 dimensions, where you take atoms and cool them down every which way, Steve described this as optical molasses, a viscous medium for the particles. And immediately you can start to think of this sort of mechanistic view of what's going on, and it kind of opens up your view as to how to describe physics, how to really understand what's going on. And, you know, once I saw this, I said, you know, this is the kind of work I wanted to do. I mean, it's a very different qualitative thing from you know, many different approaches to physics. And actually, I think at this point, to some reasonable degree, it permeates the entire field of atomic physics, which was not the case in the mid-'80s. So I just mentioned a couple other experiments that we did in those first few years at Stanford, which shows you this flavor of a ball and stick model. We did an atomic trampoline where atoms were collected over here and made cold enough that you can bounce them off of a light field at a surface. An atomic funnel where you have atoms coming in from a bunch of different directions with a reasonably high spread, a small phase-space density, a high spread and momentum, and then this little arrangement, often now called a 2D MOT, will allow you to extract the atoms much, much colder in a smaller beam at the end. All right, so both of these things are things that you can actually make a real, honest-to-God mechanical model which shows you what's going on in this atomic system. Right, I think that's something which is, you know, it's fun to do those kind of experiments, and it's fun to describe those kind of experiments. So I think one of the things which makes the work so high profile is the ability to actually go and describe them in this way, so that you recognize that as a funnel. This is actually sold now as an atomic trampoline. You can buy an atomic trampoline where you bounce little balls off of special material there. The second thing, which I would say falls in this list, is that as an approach to science, what you want to do first off is you want to develop the technology. And the technology may be a very scientific-y kind of technology, but you want to do that, and it's through that way that you can ultimately advance science. So the things that he was doing when he first got to Stanford were laser cooling and atom trapping, or just before and then after he came here. And the goal in the future was really to turn these things into precision measurements. I mean, that was really why atoms were trapped and cold to begin with. But the other thing is you don't really know, right? So the point is that you can't really start off over here. It's hard. What you want to start off is developing tools that have the possibility of ultimately yielding these advantages. And I think you'll see again and again, if you think about all the work that's been described here, it falls into this form for the stuff that Steve has done, which is that you develop a technology and you really make it good, and then you see what you can do with it. he described something like this in his Nobel lecture, where he talked about following your nose, head close to the ground where the scent is strongest. That's the way to make progress in science. I think that's been shown again and again. Another thing he taught me was that you should look at what you're doing, and there's a mundane level at which this is true, where you actually should be looking at what you're doing. You know, it's not good to be aligning optics like this. But more generally, it's that to the extent that you can actually observe, you can actually take a picture or something or look with your own eye, it's a very powerful way to do science. So Steve told the story about when optical molasses was first discovered. There was some discussion about, well, should we use a PMT or how are we going to find this? And his, one of his many brilliant ideas was, well, let's just put my head down and look into the apparatus. And there you could see the atoms, this glowing ball of atoms. Look, probably not quite as bright as that. But that's one extremely effective and interesting way to do science. And I'd say when he entered into biology, I think this is his first polymer-related experiment where the dramatic thing is just that you can actually see these single molecules. You can image them and really have this ball and stick approach to manipulating them, which was extremely novel within that field at the time. The fourth thing I learned was the Japanese management style, which is something which, I didn't learn, I sort of knew this, but he explained it in great detail at the first dinner at his house when I was a student. My wife still remembers it very clearly. Where the Japanese management style is that you have the factory workers on the floor and they're busy, and if you really want to motivate them, then the manager goes down there and also works next to them for the entire shift and maybe a little bit more to get the thing done. And that certainly, when he came to Stanford, that was the approach that he had. And I think from Leo Holberg's talk, we could see that sometimes that could be hard for people trying to keep up with Steve in the lab. Usually, also, you should always have an image when you're showing pictures. So this is the Japanese management style image that I had here. So those are the four things there. And then putting all those together brings us to this, which is in some way a summary picture of stuff from Stanford in the time that I was there. This is it's actually not a photograph, because I did, at the time, I envisioned this very talk in 1992, and I took a snapshot of this door. But it's hard to find a picture once you've had several kids, especially after that much time. So, but I'm pretty sure it was almost exactly like this. This is his office door in 1992. So someone would do a piece of work, and you get some result, something which is the culmination of a lot of work, and then you tape it onto the door. And so I'll just run through this. This here, which was just from about a year before that, was work with Markasevich, where it's an interferometer fringe, and it's the first interferometer fringe based upon a photon atom type of interferometer. And then this over here was what my thesis is actually written about, which was the first measurement of the atomic recoil. This was the first step in ways to measure the fine structure constant. These are experiments which are still going on, but here, these were the first kind of signals like this. We had imagined that this is what the signal would look like, and we took the data, and it was just like what you'd imagine it to be. You have a picture over here, also from exactly the same time period, which was the first measurement of a cold collision shift, right, which is centrally important to this entire generation of atomic clocks. This was happening right at the same time, at the end of when I was a graduate student. This is a picture showing the data of Raman cooling, where this is a novel and very powerful way to cool atoms to below the photon recoil in temperature, which was also done that year. And also we have here a picture of the culmination of Mike Fee's thesis experiment, which is improved measurement of the positronium frequency, alluded to in an earlier talk today. And that was also just pasted on the door. And I guess you might notice over here there's this other thing, which was also right there in the center of his door. And this is sort of, I think, emblematic a little bit of the loss of the Japanese management style. Because clearly Steve was very effective at getting all this different work happening all at once in his group. But you can't be at this and this and this and this experiment all at the same time. So you can't be working with the workers on the factory floor. So his time was day-to-day spent elsewhere. So this is the only thing on this page that Steve actually pasted on the door himself, and I think it demonstrates that he had a working knowledge of CorelDRAW, and he was pretty proud of it. Here. Actually, one thing that I found when I was trying to make up this slide is that, because I'm pretty sure this is exactly the picture that was on his door. He didn't even make it. He just printed it out. but he did it perfectly well. Okay, so for the last bit of my talk, I'm just going to talk about the 3 experiments that are going on in my lab, and with extremely briefly, but also with a little bit of an emphasis on the kind of things that, in the way that they, I think, relate to the way Steve goes about doing science. So one is we have an experiment where we make an optical lattice. So these are using beams at a shallow angle that interfere with each other, and that gives us a spacing of about 5 microns between lattice sites. And that forms a potential, which is a cubic lattice with a 5-micron spacing in every direction. And we do that with high numerical aperture optics, and it allows us to take a picture of, and actually this would probably be better if it's possible to lower the, just for this picture over here, if you can lower the lights for it. And this picture is a picture of single atoms, where every bright spot that you have over there is just a single atom trapped in this optical lattice. And then this diffuse haze that you can see around here are also single atoms trapped in the optical lattice, just at out-of-focus planes. So one thing we can do is we can take a picture like this, and then we could change the focus and take a picture of the next plane and the next plane, and this way determine exactly where the atoms are at each site over here. And we actually image that using the cooling light, the light which is doing the laser cooling, and that steady state temperature is well below the depth of the optical lattice. So we can take real-time pictures of this. So this is actually one-to-one video where you're just sitting there and seeing essentially nothing happens. Around the edge, sometimes where the lattice is shallow, you see an atom pops in a view or out of view. And then gradually these deplete, because every 100 seconds or so an atom, any given atom is going to get knocked out by a background gas atom. But this, that's, I'll just go back one step there so you can see it there. It's a little nicer. And anyway, I think this certainly has the flavor of what you do, and it's the kind of thing which I'd say before 1986, before 1985, it would be totally crazy to think about being able to take a picture like this. But I would say it's something along the natural progression of what one can do with this technology. And I'd say the reason we're doing this is ultimately that each of these atoms could be a quantum bit in a quantum computer that could have a lot of qubits and potentially be very accurate. Another experiment which was briefly mentioned by Eric in the previous talk, an Electron EDM Search, where there it's a whole lot of technology. I'm not going to go into any detail about what we're actually doing, but it's taking laser cooling and atom trapping and a whole series of tricks that have been developed over time and then applying them to this measurement of fundamental constant, which is really the reason that all this technology was explicitly developed in the future, although obviously it's expanded to much more. One thing Eric said that you're doing measurements like this, and at the end of the day you're happy. It's not exactly my experience with this. It's more like the end, it's more like the end of the decade. Maybe you're happy. I don't know. And the third apparatus that I have at Penn State is something where we start with a BEC and we load it into a trap which has these 6 beams in it. It's essentially a 2-dimensional optical lattice with very large beams, and what that does is it confines atoms into tubes. So the tubes would say look like this, and the tubes are capped off by these red beams which confine them axially in that direction. So here in this situation, the atoms are sufficiently cold when you load them into there that they're all in the vibrational ground state of their respective wells, and so there's no possibility of any excitation transversely. So in that sense, they are just strictly one-dimensional gases. There's no dynamics for anything except for that one direction. And in order for them to really be 1D gases, there's got to be negligible tunneling, and we can make these traps deep enough that they are really a bunch of independent tubes. So when you do that, it turns out that the interactions in 1D look like point interactions, like delta function potentials, and which makes these systems, any given one-dimensional system here, a theoretical system which has been studied since the 60s. And there's a whole lot of work on the many-body physics. It can be many-body correlated wave function physics in this one-dimensional system, in a one-dimensional situation where there's a lot of theory, but you haven't been able to experimentally realize it until you apply this technology to it. There's a lot of experiments that we can do. I'll focus on one, which I think has the flavor of the stuff I was talking about earlier, where we take these 1D gases, which the properties are exactly predictable, and we've demonstrated the properties that were predicted. We can also then take these things out of equilibrium. We do that by taking the 1D gas and pulsing on a standing wave, which diffracts the atoms from that point. It allows us to take a sample of atoms and put them in a superposition of half of them going one way and half of them going the other way. Right? So we're in a superposition of atoms going this way and going this way, very far out of equilibrium. Now, if you do that and you have a weak harmonic trap there, then you get a motion which is like this. So this would be what it looks like in position. This would be what it looks like in velocity. So the initial point would be something like this, where you start off over here and you're putting in a plus and minus v, and then the thing evolves over time. And I say this has the feature that it's very closely analogous to this well-known toy, something which everyone is familiar with, this Newton's cradle, right? Or this would be a mode of a classical Newton's cradle that looks more like the kind of excitation that we have over there. And I have videos a little bit hard to access here, but you guys all know what it looks like. It goes click, 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 and does that for a long time. So here, we make quantum Newton's cradles, and they're quantum because the particles, instead of always bouncing off each other, which the stainless steel balls always do, these often go right through each other, and sometimes they bounce off each other. And instead of just having 5 of these per, we have between 50 and 300, and we have thousands of these all in parallel with each other. And we can look at the revolution. This is what happens if you take a picture, snapshots at different points during this oscillation. So this would be the initial velocity distribution, and essentially we're measuring the velocity distribution as a function of time, and you see this oscillation of the two halves. And we can sit there and watch it for many, many cycles as it oscillates. And what we determine that even though there's many collisions that are going on, especially at these points, at the high density points in the center, there's many collisions, they don't thermalize. I mean, we set a lower limit on the thermalization. The lower limit is near 10,000 collisions where the gases don't thermalize at all. And just to compare that to, say, a three-dimensional gas, in a three-dimensional gas, it takes less than 3 collisions per particle to thermalize 1D because it's this interesting integrable system does not thermalize. So the goal here, which is not really the goal of these experiments when we started off, but the goal at least related to this part of it, is that we feel it may be possible with some theory and experimental collaboration to start to understand the real nature of irreversibility in quantum systems, in many-body quantum systems, something which has been a little bit hard to get to just by theory, and maybe with a collaboration between theory and experiment, we can get there. So in summary, happy birthday, Steve. That's my summary. And as just a lead-in to the next talks, because I was looking around for the photograph for a long time, I found some other photographs all taken, as you can tell, must have been the day I defended my thesis because I'm wearing a button-down shirt. So that's our next speaker here, circa a while ago, and then possibly the speaker after that if Mark actually has arrived, yes. Okay, so thank you very much.
Okay, time for questions. Oh, okay. Ooh, it's hard to see. I have to walk here so I actually see.
Yeah. Is this on now? Is it? Okay. It's because it's an integrable system, right? Which means that you can follow the equations. If it's an integrable system, there's a conserved quantity for every particle. Say in a 3D gas, there's very few conserved quantities. There's maybe the total energy or the total angular momentum, and otherwise everything just sort of mixes, and you get ultimately the maximum entropy state is the state that you would observe when you look at it. But over here, in an integrable system, and it's not just because it's 1D, it's because it's 1D with this special kind of potential. There's one conserved quantity per particle, which means that although it can evolve into some sort of steady state, that steady state depends upon the initial condition. It is not what you would normally think of as the maximum entropy state. So one of the things that we can do, because we have this system which is at least a very good approximation of perfectly integrable, I mean, good enough approximation that over a very long time we don't see anything happening, we can change parameters, like, say, lowering the depth of the lattice or adding some potential axially to make it so it's not strictly integrable. And then we can see this onset of thermalization that happens once that potential is varied. Once either, say, the 1D system becomes more three-dimensional, or that 1D system ceases to have interactions which are of this delta function type, which are the integrable type. They have more finite range interactions, and then they will ultimately thermalize. Right? This is a very widely studied area in classical physics. It's just that the jump from classical physics to quantum physics has really not been successful over time. And maybe that'll soon end. Yeah, so that's true, and that's a general statement about. I mean, usually I give a longer talk than this on this stuff, but I'll if you have something which is strictly one-dimensional and you have a two-body collision, then there's no way to just in that two-body collision to change the energy momentum. There's only one way that conserves energy momentum in that process. So it's true. It's not possible to tell whether if they're identical particles, whether they've bounced off each other or gone right through each other. It's just that that special thing ceases to be the case for, say, three-body collisions, unless you have an integrable potential. So really, when you're looking at it, in detail, it's a little misleading to just try to calibrate, try to count things in terms of these two-body collisions. The fact is, these are strongly interacting gases, and there are also many higher body collisions, and those will thermalize unless it's an integrable system. Three-body collisions but for an integrable system, three-body collisions do not thermalize. Right? Four-body, five, it doesn't make any difference. Everything comes down to three-body collisions, and that's not sufficient to put you into a what you would call as the traditional equilibrium state. So yeah, that's something which is not at all obvious, and if you make it not a delta function, if you make it a finite range interaction, it would not be the case anymore. But if they're delta function interactions, it doesn't make any difference how many particles are involved, it won't thermalize. I mean, there is a reasonably simple picture. I mean, if you want to say what happens, which is that three momenta come in, and the only way to actually, the dynamics only allow then those same three momenta to come out of every individual collision. Right? It's just, if you want to write down the more detailed explanation, it actually gets pretty involved. And I'd say, this is something which is true whether you have a weakly coupled one-dimensional gas or a strongly coupled one-dimensional gas, right? And it's true whether it's quantum degenerate gas or whether it's a thermal gas, right? So it's a feature really of the nature of this potential, and which is special to one dimension. It's not a feature which is related to what you might otherwise think, like the fact that it's started off as a BC. That's not the important thing.
So I think it's getting too deep into the details. I think we have to...
Unless someone has a very general question.
Move on. Okay, and maybe we can actually have collective questions later on.